Hey everyone, welcome back. Today we're looking at a paper from Google DeepMind called ELT, Elastic Looped Transformers for Visual Generation. It's about making AI image and video generators dramatically more efficient without sacrificing quality. And the core idea is surprisingly elegant. Let's get into it. Latest AI image generators have gotten incredible. Systems that can generate photorealistic images, videos, artwork, things that would have seemed impossible just a few years ago. But here's the catch. These models are enormous. The most powerful image generators have hundreds of millions, sometimes billions, of parameters. More capacity means more memory, more cost, and harder to deploy. So researchers are always looking for ways to get the same results with less. Here's the key tension in AI model design. You want your model to be deep, many layers of processing, because depth gives it the ability to learn complex things. But more layers means more unique parameters, which means more memory. These two things are usually tied together. What if we could decouple them? The idea of looped transformers is simple. Instead of having many unique layers stacked on top of each other, what if you just reused the same small block of layers multiple times? Loop through them over and over again. You get the same amount of computation, but with far fewer unique parameters. Your model stays compact in memory while still being able to do complex processing. ELT applies this idea to state-of-the-art image and video generation. But there's a problem with standard looping. If you train a model to loop exactly 8 times, it learns to produce good images after exactly 8 loops. Run it 4 times, and the output is a blurry mess. Run it 10 times, and quality actually degrades. The model creates useful internal states only at the very end. Everything in between is kind of in limbo. It's a fixed-depth system, pretending to be flexible. This is where ELT's key contribution comes in. Intra-Loop Self Distillation, or ILSD. The goal is to make every loop count produce a meaningful result, not just the last one. And the way they do this is clever. They use the model itself as its own teacher. During training, ELT runs 2 paths simultaneously through the same shared parameters. The first is the teacher path. It runs the full number of loops and produces the best possible output. The second is the student path. It exits early at a randomly sampled, shorter loop count. The student is trained to match both the ground truth labels and the teacher's output. Over time, this forces the shared parameters to compress useful information into earlier stages. And crucially, this adds 0 extra parameters. It's just a smarter training strategy. The result is what the authors call anytime inference. Once trained, you can run the same model with as many or as few loops as your hardware allows. Need a quick result on a phone? Use fewer loops and get a decent image fast. Have a powerful server and want the highest quality? Use more loops. One model, adjustable compute. No retraining needed. So how well does it actually work? On the standard image generation benchmark, ImageNet 256 by 256, ELT achieves an FID score of 2.0. FID measures how realistic generated images look compared to real ones. Lower is better. This matches MaskGITXL, which is the previous state-of-the-art. But ELT does it with just 110 million parameters versus MaskGITXL's 446 million. That is a 4x reduction in parameters, at the same quality and the same compute budget. For video generation, ELT also matches MAGVIT on UCF101 with the same 4x parameter savings. ELT also scales well across model sizes and architectures. The paper tests everything from small models to very large ones, and the efficiency advantage holds throughout. And ELT isn't locked to one type of model. It works with both masked generative transformers and diffusion transformers, the 2 dominant approaches in visual AI today. The paper also notes that ELT is orthogonal to few-step methods, meaning you could potentially combine both for even greater efficiency. There are a few things to keep in mind, though. If you use too few unique layers, like just one layer looped many times, quality drops because a single layer doesn't have enough representational capacity to capture complex patterns. And if you push the loop count higher at inference than you trained with, the model degrades because it goes beyond its learned convergence regime. So there's still some calibration needed when deploying for specific hardware targets. ELT is rewriting the efficiency standard for visual AI. It generates images of the same quality with far fewer parameters and lets you freely adjust compute resources to fit your budget. That's it for today. See you in the next one.